Can everybody hear me?
Yes.
Okay.
So I will just finish introducing you and leave the stage to you. Great, Jana. Welcome. So his primary research focus is at the intersection of machine learning and electronic design automation. Specifically, explores the synergy between these two mutually beneficial areas. Jana's research has been recognized with a number of awards, honors, and distinctions. I will just mention two: 2019 National Science Foundation Career Award and 2021 Best Paper Award from ACM Transaction on Design Automation of Electronic Systems. And Jana, thank you for joining us and welcome, and stage is yours.
All right. Yeah, thank you, Mark. So I'm very excited to be talking about some of my research on how to use machine learning to accelerate electronic design automation. As Mark mentioned, I'm a faculty member at Washington State University. So let me start with some motivation and take-home message before I start talking about technical details. So we are seeing an exponential growth of emerging applications right from the edge and mobile platforms like augmented reality, virtual reality, robotics, self-driving cars, smart health, and so on. So we require innovative hardware designs to meet these emerging edge applications. Similarly, on the big data applications end, the machine learning workloads are increasingly becoming. Yeah, go ahead.
Jana, I think that you are not sharing the presentation mode.
I think I shared in the presentation mode. Is this not presentation mode?
No. Maybe you need to switch if you are in duplicate windows.
It's I have. This is the only window I have actually right now. Let me see. Okay, I'm seeing this, but I don't know why. I'm using actually the presentation mode. Is this still not the same?
No. So try stop sharing and share again. Maybe it will.
Okay. Let
It
me
will
try.
fix the problem.
Okay. Stop sharing, and then again screen share, and then entire screen. Okay. Share. Okay. I'm sharing now, and let me try it again. Does this work?
Yes.
Okay, fantastic.
Thank you.
All right. So I was just mentioning that there are these emerging applications from edge that we talked about, and these are increasingly becoming more complex also. So we require innovative hardware designs. But at the other end of the HPC applications and big data applications, machine learning increasingly is becoming more complex, and we are training them on much more larger training data sets. And similarly, the real world graphs are increasingly becoming more complex and large. And similarly, lots of scientific data from genomics to medical informatics. The data is increasing. The algorithms are becoming more complex. So we require innovative hardware to meet the needs of these emerging applications. So the design requirements for a hardware platform, of course, depends on the application scenarios. So what would meet the application requirements on the edge would be something different when compared to you're looking at HPC applications. So what objectives you want to optimize, what constraints you want to satisfy. And there is a specialization gap here. So the gap between the off-the-shelf hardware trends and the application needs. There is increasingly growing. This gap is growing, and to meet this gap, if you want to design application-specific hardware, it remains an expensive and difficult process. This was actually laid out as a very fundamental challenge in this vision paper from Louis C.J. Markhill and colleagues. So machine learning is actually an attractive solution to essentially solve this particular problem that we mentioned. Okay. And with that, I will give the take-home message before I talk about technical details. So one thing is that whenever we want to use machine learning, we should not think about machine learning as a magic wand. I'm a trained machine learning person, and I have been exploring EDA problems for the last 6 to 7 years, and I can say that machine learning is not magic. And oftentimes, off-the-shelf machine learning solutions may not be the best solutions to tackle electronic design automation problems. So often, you can be more creative about how you formulate your problems. And sometimes there is a lot of useful structure in the problem that can be exploited to devise very effective and efficient algorithms. And you want to always use domain knowledge from the designers. Before even machine learning became popular in electronic design automation, the designers have been designing hardware for the last 3 4 decades, and they have lots and lots of knowledge. So we want to definitely use the domain knowledge. And here I have this phrase which says, an ounce of knowledge is worth a pound of training data. Okay. And then we want to build analytical models or statistical models of the design objectives, and we want to use them to perform intelligent and efficient design space exploration, right? So this is the take home message of my talk. And with that, I will try to kind of give you some dive into technical details to justify this take home message. So the context of this talk is we are looking at machine learning and data-driven methods to accelerate a variety of decisions that we make depending on the design scenario. So whether it is IoT or mobile or embedded or HPC applications, what kind of hardware design decisions we are going to make. And there are two kinds of optimization problems. So one kind of optimization problems is the design time. So here, if you look at compute layer, interconnect layer, and the memory layer, you are looking at these holistically and trying to come up with overall system design that optimizes certain objectives and meets certain constraints for a set of target applications. So this is everything that you do before basically manufacturing and chip fabrication. Now, the other kind of decisions you can also think about is this runtime optimization. So you could think about resource management, how to map the tasks, how to schedule the tasks, how to adaptively route the data, and how to do power management as a function of the application workloads that are being run. So this talk is primarily going to be about design time optimization, not the runtime optimization. So with that, the outline of the talk is I'm going to basically talk about the design time optimization problem a little bit and what challenges are. And then I'll use many core design, which is where I have done a lot of work over the last 4 or 5 years. And I'm going to talk about a simpler case of how to use analytical models of design objectives to perform optimization. And then I will build on that to talk about some advances in Bayesian optimization that were primarily motivated by EDA problems. So much of this machine learning research and new machine learning research was motivated from EDA problems. So let's talk about design time optimization. So when we look at design time optimization, there are three key elements of any design time optimization problem. One, design space, right? So this could be continuous space. So this could be like each design could be a point in a Euclidean space. And similarly, one thing that Daniela mentioned in the previous talk is a lot of the EDA problems, the design space is not continuous. We have these combinatorial structures and hybrid structures, which is basically a mix of discrete and continuous variables. Now, the other element of the design time optimization problem is what kind of objectives are we looking at? Are we trying to optimize a single objective like energy delay product, or are you trying to optimize multiple conflicting objectives like power, performance, area, thermal, and so on and so forth? Now, the other aspect is that how are you going to evaluate these design objectives for any given design in the design space? Are you going to use some cheap heuristics or designed by the designer, or are you going to perform expensive simulations using cycle accurate simulators? Okay. And the last thing is the design constraints, right? So these could be like analytical or declarative constraints in the computing science terminology. So for example, in a many core chip, you want all the cores to be connected, right? Because otherwise they cannot do data transfer between them. And also there is other kind of constraints that you don't want the routers to be too fat. That's actually a very bad physical design. So those are constraints. You can actually write them down in declaratively, but there are certain constraints you cannot write them down analytically. For example, you want the peak temperature to be below a certain temperature, and that you cannot write as an analytical constraint, and you have to simulate the design to be able to actually see and observe what the peak temperature is going to be. So bottom line, the key challenge in most of the design time optimization problems is that you have to perform these cycle accurate simulations to evaluate designs, which are actually very, very expensive. So there are two key challenges in design space exploration problems. So one is modeling. How do you build models, to guide design space exploration? And the second challenge is reasoning. How do you use these models to perform intelligent design space exploration? And I'm going to talk about both of them. So with that, let's talk about many core design as a combinatorial design optimization problem. And we will be using analytical models of design objectives in this case based on some workload analysis that you profile the application. So before we talk about any of the algorithmic challenges, a concrete problem, many core design optimization problem. So you have a bunch of cores and routers and communication links, and you want to place these cores and the routers and the communication links to meet some constraints, like the network should be connected, and this chip needs to be optimized for some target applications, and you're probably looking at optimizing multiple objectives like performance, power, and thermal. And whenever you're looking at multiple objectives, there is no one good solution that will optimize all the objectives. So what we are looking at usually is some trade-off or some kind of a Pareto set of designs that optimally trade off the objectives that we want to optimize. So in our case, each design is a placement of cores, routers, and the communication links. So here is a very concrete illustration. So here we are looking at a 3D system, a 36 tile system. And let's say you have 4 CPUs and 8 LLCs and 24 GPUs. And you have this 3 by 3 by 4 configuration. So you want to place these cores and LLCs on this system. And also you want to optimally place the communication links between these cores. And once you have, this is the design space, each design, the corresponding placement will be a point on this particular Pareto front, right? So each point corresponds to a certain power, performance, area kind of evaluation. And what you are interested in is this Pareto front, which is shown in the as a sequence of red points. Okay, so this is basically the optimal trade-off among the objectives that you care about. And here, just for pictorial illustration, I'm showing you for 2 objectives. So some of the challenges, like Daniela mentioned, the designs are actually graph structures, right? So you have these nodes placed, and then there are these communication links connecting these nodes. And these are combinatorial because there are many possible ways to place these objects. And the design spaces can also become large depending on the system size. So if you have 64 cores versus 1024 cores, the design space grows significantly. Similarly, if we introduce new and emerging integration technologies like monolithic 3D, where the routers and the cores can be designed spanning multiple tiers, then the design space grows significantly as well. And the other challenge is that the evaluation of designs is, you require these computational simulations, which are very expensive. And often, in practice, what people do is that once they have an application workload, they kind of try to profile the workload and try to design some analytical models of the workload to design various objectives. design objectives, and then they optimize. Okay, so you can think about these as kind of a heuristic way of design evaluations to identify promising designs. And once you identify these promising designs, you can actually do an intelligent search over them using cycle accurate simulations. So as I mentioned, there are two ways to go when you have these analytical models to expensive simulations. So you can do all your optimization using the analytical models and identify a very promising designs, and then you can actually do an intelligent search among those promising designs using the expensive simulation. So that's one way of going about it. The second way of going about it is you can think about the analytical model as a low fidelity design evaluation. So here, when I say low fidelity, essentially it means that it's a cheap evaluation, but it might not always be as accurate as an expensive simulation. Whereas the expensive simulations, when you use the cycle accurate simulators, you get not only very accurate evaluation, but it's also very expensive in terms of the resource cost. So you can use these both fidelity evaluations to pose a multi-objective design optimization using these multi-fidelity design evaluations. Okay, so I'm going to talk about the first part first, and then I'll talk about the second part in the second half of my talk. So like I mentioned, if you're using analytical functions to evaluate designs for performance, power, and thermal, you can actually perform a computational search guided by these objective functions. And if you have single objective that you want to optimize, you have your standard algorithms like simulated AnyLink, genetic algorithms, and the multi-objective extensions like AMOSA and NSGA2. So these are like the workhorse in the EDA community. But one common drawback of these particular methods is that they do not learn from the designs that are explored in the past to explicitly guide the future exploration. And when you can use machine learning to actually overcome this drawback, and that's how we call it ML guided design space exploration. So the key idea here is that you can learn some form of search control knowledge based on your past search experience and use that learned knowledge to filter out a big part of the design space that's probably not going to be very promising, and you can focus on the more promising regions. And if you think about this as a theoretical principle, essentially you are doing active machine learning to optimize the overall search to get to really high quality solutions. So in our research, we have actually studied a couple of algorithms, MoveStage and Moose, and in the context of local search procedures. And both of them have the same principle that I mentioned. And I'm going to talk about one particular algorithm, which is the MoveStage. So it's an iterative algorithm. Essentially, you are doing a local search. So what you do is, in each iteration, you actually start your use your current evaluation function, which might not be as good in the initial iterations, to select a good starting point. And once you do select the starting point, you start your search guided by a Pareto hypervolume heuristic, because we are looking at multi-objective optimization. And by the end of the search, you will realize what kind of PHV you are achieving in terms of the local search, local optima, and then you can use that to generate new training data to improve your evaluation function for the subsequent iterations. So it's kind of an iterative loop where you do more search and you generate more training data to improve your evaluation function. So as iterations progress, your knowledge will improve, and you will do better and better search in the promising regions of the design space. So with that, let's look at each step of this particular algorithm. So the first step is really selecting the starting states using the evaluation function. So the evaluation function is doing some kind of a local search. So it starts from certain design and it evaluates its neighbors and picks basically the most promising region in the design in the neighborhood. And you keep doing that until you hit a local optima. Okay. And now this local optima state would be the one that you will be using to start your local search. Now you start from the state that you actually have selected, and from here you will basically look at the neighborhood of this state and which one actually gives you a better or the best Pareto hypervolume, and you keep doing this hill climbing steps until you reach the local optima where you cannot improve. So this is the local optima, and the local optima now says that your Pareto hypervolume, which is the quality of the Pareto set solutions, is 0.89. So now what you do is, if the evaluation function was actually trying to say that if you start from this starting state, your Pareto hypervolume will be certain value. And if that value doesn't match with what actually was observed, then you can create a regression example by saying, okay, the input is the features of this design and the output is what is the value of the local optima. And the nice thing is that you can generate one training example for each state on this highlighted red region, because anywhere you start on this local search trajectory, you are bound to end up at this local optima. Okay. So you generate a bunch of regression examples from this local search trajectory, and then you give it to the you give the aggregated training data from all your past explorations to this regression learner, and you get an improved evaluation function. So let's look at some experimental results. So this is basically one experimental scenario where we are looking at this 36 tile system, and we need to place these course and communication links to optimize multiple objectives. So here I'm showing you three results. The first result is, as a function of the time, I'm basically plotting the Pareto hypervolume, which is the quality of the multi-objective solutions or the Pareto set. And here we are comparing AMOSA and MOVE stage. And as you can see, the MOVE stage quickly converges to very high quality solutions. And even after a very long time, the MOVE stage doesn't catch up in terms of the the quality of the solution. So we see around 9x speed up in optimization time to get the same solutions. The second result I'm going to show here is that as we explore more and more designs, our evaluation function, which is the knowledge that we are learning, it is becoming more and more accurate, and its prediction error is almost close to zero, which is what you want to see. And the third result I'm going to show is that, well, okay, the Pareto hypervolume is improving, but that's not what an EDA designer cares about. EDA designer cares about temperature delay product or energy delay product and those kind of things. And as you can see that, MOVE stage solutions are significantly better compared to the solutions you got from AMOSA in terms of even the normalized thermal delay product. And the nice thing is that, the speed up and the quality of the solutions that you get from MOVE stage actually improves as the number of objectives increase from 2 to 3 to 4. The effectiveness kind of increases, and also the effectiveness increases when the design space starts growing. Okay, and the key thing to note is that even if the AMOSA is given a significantly large amount of time, it doesn't reach the quality of the solutions that MOVE stage produces, partly because it gets stuck in local optima and it cannot come out of it. So as I mentioned, one very interesting consequence of this result is that if you have these emerging technologies like monolithic 3D, where the routers and the cores can be extended over multi-tiers, you have the potential to come up with better mini-core designs. But at the same time, the design space grows significantly, and the design optimization problem becomes much more complex. So I would conjecture that MOVE stage and MOVE's kind of ML-guided design space exploration approaches will be very effective in these kind of complex problems, even beyond the TSV-based integration systems that we just looked at. So now you have used these analytical models of the design objectives, and you performed your design optimization, and you got your more promising designs that you have explored. And this may not be the best solution because your analytical models may not be accurate. So now what you can do is that you got these promising designs, and now you can search in these promising designs to figure out what is the right solutions guided by these expensive simulations. So whether you take the first approach or the second approach, Bayesian optimization is a very effective framework to solve either of these approaches. Okay, So I'm going to basically briefly talk about what Bayesian optimization is and what the key ideas are, and then I'll try to talk about how EDA problems push the frontiers of Bayesian optimization so that we require much more innovation on the machine learning side. All right, so advances in Bayesian optimization. So let's quickly go over the background on Bayesian optimization. So it's basically Bayesian optimization can be used anywhere we want to search a huge design space guided by some expensive evaluation. So you have basically f of x, which is basically expensive to evaluate. Looking at an capital X, which is the design space, and you want to find the best design in this design space according to this function f of x. Okay. So there are two things that you need to note in this problem setting. First, f of x is kind of a black box. So you give an input design x and you get an f of x, which is the design evaluation. Okay, you don't know anything about the structure of the function, or how does the function f of x look like from a mathematical structure point of view. The second thing is that each call to this function is very expensive. So imagine, instead of this black box, you have a cycle accurate simulator where you're passing as an input a design, and then you produce the design evaluation. So that's the picture that I want you to have while you think about this setup. The key idea in Bayesian optimization is you build some kind of a surrogate statistical model like a Gaussian process, and you use it to intelligently search the space. So based on all the training data that you have so far, you build this statistical model and then use the prediction and the uncertainty of the model to define basically what is called an acquisition function or a utility function that basically tells which designs I should be evaluating next so that I will reach my goal of finding the optima as quickly as possible. So once you have defined this utility function or the acquisition function, this is kind of a cheap optimization problem because you are basically using the statistical model to evaluate this utility function. And once you select what is the most utility design that I should be simulating, then you actually go ahead and do the design simulation, and you get a new training example that tells you, okay, if this is the design, this is what the design evaluation is, and you update the statistical model and you repeat this loop. Okay. So as I mentioned, there are three key elements in Bayesian optimization. One is the statistical model. So you can use Gaussian process, or you can also use Bayesian neural networks or Bayesian graph neural networks as your statistical models, because you require your prediction, but also you require uncertainty. The second thing is you require an acquisition function or a utility function. So you can use expected improvement or upper confidence bound or Thompson sampling, these kind of acquisition functions. And then you need also an optimizer to optimize the acquisition function. So typically it's a gradient-based search in the context of continuous spaces, and it's a local search if you are looking at combinatorial spaces. So the unfortunate thing with the BO is that much of the BO work is actually done on continuous spaces, and it's only done on single objective optimization. So there's a lot of really good work in this particular space. But unfortunate thing is that most of the EDA problems don't fit the current work in the machine learning. So the EDA problems, the design spaces are combinatorial or hybrid spaces. And we are often interested in optimizing multiple objectives where there are trade-offs between power, performance, area, and thermal objectives. And similarly, we don't have single fidelity optimization. We have multi-fidelity optimization where we have simulations of different granularities that vary in the resource cost and the corresponding accuracy of design evaluation. So the rest of my presentation, I'm going to talk about this modeling challenge and the reasoning challenge to solve some of these frontiers of BO problems. So let's look at combinatorial spaces. So where you have looking at permutations of objects or some kind of graphs as in the many core design. So in a recent paper, we looked at a Gaussian process as the statistical model. And whenever you want to use Gaussian process as a statistical model, you need to basically specify a kernel that captures the problem structure. So a kernel is nothing but if you have two designs, it basically tells you how similar these two designs are. Okay, so the diffusion kernel is a very nice foundational concept in machine learning, which is actually very appropriate for discrete structures. So it's defined based on the Laplacian of the graph, where the graph is over the entire combinatorial space. So each node is actually a design, and you're talking about how similar two nodes are, or two similar designs are, and you're looking at the entire graph to capture that similarity. So the key idea behind this particular thing is, any kernel will have some kind of, underlying feature representation. For example, if you think about RBF kernel, which is basically a continuous diffusion kernel, you have what is called random Fourier features that can actually approximate the kernel. But you don't have such features for discrete diffusion kernel. And in this particular work, we have defined what those features look like by exploiting the structure of the graph. And the nice thing about these features is that not only now the statistical model becomes more tractable, but now you can actually sample functions from the GP posterior, and that is actually a missing puzzle in in the Bayesian optimization literature. Okay, so once you have these master features, you can think about, well, I can leverage all of the work on the BO for continuous spaces to actually design more effective BO algorithms for discrete or combinatorial spaces. So here I'm going to talk about one particular example of this BO over discrete spaces in a recent paper that we have. So here, we were trying to basically look at a hardware and software co-design problem. We were looking at a heterogeneous many-core design with RERAMs and GPUs to accelerate CNN training. And one of the important things here is that RERAMs are very fast with respect to multiply and accumulate operations, but they don't do a really good job in terms of the batch normalization layer. So here what we looked at is, well, can we find neural architectures by optimizing the BN layers so that we select which BN layers are really critical, and they will give you the same performance as you have all BN layers. Okay, and to actually do that, you have to perform training with different neural networks architectures, and that's actually a very costly process. So you're essentially looking at whether to have a BN layer or not after every convolution layer. So it's a problem over binary structures. So a perfect candidate for BO. So we actually found that most BN layers are not necessary. So, as you can see, you can actually get the same accuracy as all BN, but with a significantly less number of batch normalization layers. Okay, so now what would be the hardware physical perspective of this particular software result? The physical perspective is that if you look at a many-core design with both GPUs and RERAMs, now with few BN layers means you don't require as many GPUs, so you can actually use those resources to have more RERAMs on the chip, so that you can actually improve both performance and energy efficiency. And as this result shows, we get about a 15x speed up compared to a GPU version of the CNN training. Okay, so again, a hardware software co-design going about the neural architecture search. Similarly, for hybrid spaces, when you have mixture of discrete and continuous variables, there is no existing Gaussian process model because nobody knows how to design kernels for these hybrid spaces. So in a recent ICML 2021 paper, we actually gave a solution for this particular challenge. So for example, first of all, you might ask, where does hybrid spaces actually appear? So for example, in analog circuits design, you can think about the topology of the circuit as discrete and the circuit parameters as continuous. So how do you model the interactions between these discrete and continuous variables? It's a very hard and open problem. So the solution that we had was we have constructed what is called an additive hybrid diffusion kernel, and it exploits the general recipe of additive kernel. So what you do is you assign each of your discrete variable and continuous variable a corresponding kernel. So in this case, we have used the diffusion kernel, and then you consider all possible interactions between those variables. Okay, so first order, second order, third order, all sorts of interactions, and then there is a corresponding weight associated with the strength of the interactions, like which interactions are more important for this particular problem. And you can actually learn these parameters in a data-driven manner using a Bayesian formulation. And one thing that we also showed in the paper was that this kernel is actually universal, which is basically a very important requirement when you are modeling. So what it says is that given enough data, this kernel will allow us to actually learn a statistical model that can capture any black box function over hybrid spaces. So with that, I'm done with the modeling. Let's talk about reasoning for multi-objective, multi-fidelity, and the black box constraints. So when you look at multi-objective Bayesian optimization, the key challenge is this is the optimal Pareto front. And we want to find this optimal Pareto front for these two functions with the small number of design evaluations. So which means that you have to select a sequence of designs so that you get this red Pareto front as quickly as possible. So this is like the standard BO loop, but now you have two functions instead of a single function or more than two functions. Okay, so how do you design these acquisition functions? So in NeurIPS 2019, we have designed this algorithm called MESMO, which stands for Max Value Entropy Search for Multi-Objective Optimization. And the key principle here is we select the design for evaluation that maximizes the information gain about the optimal Pareto front. So there are two kinds of Pareto sets here. So one is called Pareto front, which is looking at the solutions in the output space, and Pareto set, which is actually looking at solutions in the input space. Okay, so here each point is some power performance value for a particular design. So that's what we are looking at when we say Pareto front. Okay, so here is a little bit of a math, but one nice thing about this particular acquisition function is that it's actually gives us a very tractable solution, because there is a lot of underlying structure in this particular problem, which gives us a closed form solution for the utility function, which means that it's very, very scalable and very accurate. And actually in the paper, we also give a proof for the regret bounds. In fact, this is actually the first proof for regret bounds in the context of multi-objective BO. So what regret bound says that asymptotically, your solutions would converge to the optimal solution. Okay, that's the best that you can give. You cannot give a finite sample guarantee. So here is one illustrative solution result for network on chip design problem. So on x-axis, you have the number of NOC designs that you have evaluated, and on y-axis, you have this hypervolume difference, which is the quality of the solution, or the R2 indicator, which is also another metric to capture the multi-objective solutions. Okay, and as you can see, the different variants of MESMO actually does better, meaning they find better solutions with less number of design evaluations, which is the most important point. Now, here is the multi-fidelity, multi-objective BO setting. So if you look at this particular plot, on x-axis, you have two variants, single fidelity and multi-fidelity. On y-axis, you have single objective and multi-objective. So this particular quadrant, which is what we are interested in, there was no prior work. And in fact, in a recent IIII paper, we kind of gave the first algorithm to solve this problem. So the key solution here is that we extended the MESMO algorithm to take into account the information gain per unit resource cost. So essentially what we are asking is, for every ounce of information that we get, how much resource cost we have to spend. And we want to maximize that. So which means that you are trying to reach the solutions by minimizing the overall resource cost of the design evaluation. So this could be simulation time in the context of EDA problems. So a couple of interesting scenarios for this multi-fidelity, multi-objective BO. Often we have to do a lot of hardware, software co-design applications, either for training or inference and so on. So for example, you have to do neural architecture search and the hardware design search for optimizing power, execution time, and accuracy for DNN inference. Similarly, you can look at ReRAM-based accelerator design for DNN inference to optimize accuracy, area, energy, and execution time. And I'm going to present one concrete result in that will appear in ICCAD later this year. So here we were looking at RERAM design space, where we have this RERAM cell configuration, operational frequency, temperature, and the crossbar size. And the output objectives are inference accuracy, area, time, and energy. Okay, and here we were really looking at the non-idealities in terms of stochastic noise for RERAM and how to find the right configuration of the RERAM to achieve or optimize these objectives. And as we can see here, by leveraging the multi-fidelity simulations here, so here the multi-fidelitiness is that we actually don't do training on the entire training set. We actually select subsets of the training data to reduce the overall cost of the experiments. Okay, and as you can see that the leveraging the multi-fidelity evaluation, you're able to reach actually better solutions by spending less computational cost here. And this solution, the BO solution, is much better compared to MSGA2 and random search. Now, the last setting that I want to talk about is what is called constrained multi-objective BO. So oftentimes in a lot of EDA problems, you have expensive black box constraints corresponding to safety constraints. So for example, in analog circuits design, you have some constraints on output voltage or minimum inductor current. Or in the mini-core design, you have constraints on the peak temperature. And you cannot evaluate the designs unless you do actually simulations. Okay, so the key idea in this particular algorithm, again an extension of the output space entropy search principle, is you learn statistical models of the constraints that you have evaluated for the designs in the past, and you use these learned models to reason about which designs are more likely to be satisfying these constraints and which ones will have promising design objective values in terms of power, performance, and thermal. So again, this is a very simple loop that actually kind of describes what this algorithm does. I'm not going to go into the details in the interest of time. Here, basically, I show you this analog circuit design results. And as you can see, the MESMOC algorithm finds really high quality solutions by using a small number of design evaluations. Okay, and you can actually get high quality solutions by saving around 90% of the design simulations compared to traditional solutions. So which brings me to the take home message. Again, I'm repeating, machine learning is not a magic wand. Often you want to use domain knowledge, careful problem formulation, exploit the structure in the problem, and you will have much better algorithms. And to conclude my talk, machine learning and big data analytics benefited from tons of work the EDA community has done over the last 3-4 decades. And very recently, in the last decade or so, the EDA community has been using machine learning and data analytics to improve design tools. But there is a lot of need for new ML techniques, like I have mentioned in my talk. And there is a nice symbiosis relationship between ML and EDA, and I'm hoping that over the next decade, together, as we as a community can exploit this synergistic relationships. So with that, I would like to thank my PhD students who did all the work, and my excellent collaborators, Partha, Krish, Helen, Radu, Diana, Umit, and Paul Bogdan, and my funding agencies for funding this work. And I'm happy to take questions. I'm not able to hear you.
Can you hear me now? Okay.
Yeah, I can hear you. I can hear you now.
Okay. Okay. Thank you. So thanks, Jana, for great talk, and let's listen for some questions from the audience. Yes. I can see people in the lower bar, but I'm not sure that. Unmute yourself and ask. Okay, there is a question in the chat from Chithu Rupa. Bayesian optimization in high-dimensional space has typically not given good results.
Yes.
Have there been advances that address this?
Yeah, excellent question. I think that I was about to actually talk about that, but I didn't had enough time when I was preparing. So yes, you're exactly right that in high dimensional spaces, BO actually hasn't given as much good results. But one way to kind of address that is you can use this notion of deep generative models to learn very good latent spaces, and you can actually do the BO in the latent space instead of actually the original space. So the latent space would be kind of a dimensionality reduction technique where you can actually use much more effective algorithms. So even there, if your dimensionality is still large in the latent space, there is only so much that you can do. So yeah, definitely that's actually a frontier, and I think machine learning community kind of knows it, and we are working hard on it. Excellent question.
Great. So I have another one. We are a little bit off the time, but let's keep with it, I hope. So your surrogate function depends on the quality of the data that you give it, that you train it with. So if you don't have much data, then it will be less accurate, and if your data is biased to some area. So in this sense, how can you still use it when it is lightly trained, and how do you balance in this sense between the exploration and exploitation?
Yeah, so that's actually the heart of the Bayesian optimization methodology, where you are actually trying to trade off exploration and exploitation in a principled manner, because you are collecting your training data to improve the model in such a way that your model will help you get to the optimized designs as quickly as possible. So the utility function that you are defining, or the acquisition function, actually captures which data you should be actually collecting so that you improve your model in such a way that the model actually guides your search towards the better designs. Yeah.
Okay, so thank you. Last option for another question. So if not, let's thanks again, Jana, for your great talk. So thanks again. And I welcome you to continue the discussion in the social rooms. You can find them at the left bar. There are some